you want, we can just go by this like question by question. I don't really I don't know.
The learning objectives that
Uh
they have on here would definitely be, or at least the first, second. Yeah, some of these learning objectives would be definitely important stuff for me to go over. So, if I'm remembering this right. Okay, so are you familiar with the term ghost voltage?
that sounds like something from Danny Phantom. No,
Okay,
I'm not.
maybe your journeymans go by a different term. Have you ever been on the job site and you've got some wire where the circuit is turned off, but it still has some voltage in it?
Yeah, it's leftover voltage. S- um, like sometimes it's from a capacitor leaking out. Like it's releasing excess voltage.
That's one
I
one
mean,
one one
I,
possibility. So there's another thing that can happen, which is when you've got too many wires that are running alongside one another. When a bunch of those wires all have current going through them, but one of them doesn't. You remember how when you've got current moving through a wire, it has that magnetic field around it,
yeah,
that changing magnetic field. So,
yeah,
and you know how basically a transformer, the way it works is it uses that changing magnetic field to induce power in the other side of the coil, right?
hmm
Same thing. If you've got a bunch of wires, just normal wires running through to power stuff, and a bunch of them have power running, your AC alternating current, if you have another wire too close to them into that cluster, it's going to do the exact same thing as a transformer. It's going to make that, it's going to induce that current, that voltage on that line, even though that circuit is turned off.
yeah.
So an inductor is basically it's effectively just a bunch of wires that you're deliberately using to cause that effect.
Okay.
But specifically for the book's definition, it's a coil of wire wrapped around some sort of core, which is usually just a metal rod.
Yeah,
You
yeah.
can,
Like how Roland made that pseudo motor in
oh,
his
that's
shitty
right.
video.
Right, I remember that. But yeah, like
Yeah.
there's one example that my dad showed me a long time ago. It was just like I was a couple of years old, and he was just showing me like random crap. He took a screwdriver and he coiled just some random wire around it, and he hooked it up to a battery, just a little like it was like I don't know, like a D cell battery or a 9-volt battery, something like that. And then he just started using it as a literal magnet. He made an electromagnet just out of random crap from the garage.
Hmm.
But it's a pretty similar concept. But in this case, you're using an alternating current because that change in the current is what makes that magnetic field.
Right.
But that is induction right there.
Okay.
I might as well go ahead and just pull up the quiz itself and actually go over a few things. Let's review.
Looks like I was doing the quiz a while ago, and I have the first 13 done. I don't know. Uh, like, so I'll do the quiz once,
Uh-huh.
and try, and then I'll go over and I'll write down the question and the answer in full in my notes,
Mm-hmm.
and then wait a couple days and then try it again without using my notes to see if I've retained any of this knowledge. Spoiler alert, I haven't. Uh,
Okay. Was there anyone between 1 and 13 you had a lot of trouble with in particular?
I don't know, honestly. I haven't looked at it
Okay.
in a minute.
Do you have them
You
on
know,
hand?
yeah, yeah. No, I'm looking at them right now.
Okay.
They're yeah. Um, duh, 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 duh. See, I'm just clicking it through real quick. No, all these I've still got. I'm pretty sure they're right. I'll need to obviously finish my attempt before I uh know for sure. Let's see here. I'm just clicking through the questions to see if anything I'm just like, what the fuck about. Sorry. I wish I was more prepared.
No, that's fine. I didn't even prepare for this either this time around. I'm just kind of winging it here.
Yeah, man. I'm sorry. What's the deal with this time constant thing?
Time constant. Okay. Let me pull back just a little bit here. I remember.
It's question number 22 is asking about the formula for time constant.
Time constants. Okay, so in one of the previous chapters for AC, it was one of the AC quizzes we had where you were using a formula to figure out the exact voltage at any given point in time. Actually, no, I'm sorry. It was, if I'm remembering right, this formula is exactly the same as one of the previous formulas we had. Let me just go back a little bit here, because I know I wrote it down a little bit further back. Okay, AC Theory Quiz 1. So your formula, I'll give you the answer first and then I'll explain it. So your formula is right there, which is T is equal to L over R. So your time in seconds is going to be equal to your inductance, that's L measured in henries, divided by your, I believe that's resistance. Yeah, that was resistance. But yeah, if I go back a little bit, I know I wrote that down in one of the previous assignments here. I took a really quick note on it.
We've basically not been in class for like 5 weeks.
Yeah, I know.
And, you know, so like part of me is thinking I should go back and do all of the other old work again. Just to get reacquainted.
I know I wrote it down somewhere. You know what? It might have been in my other notebook because I did just start up a fresh one because I ran out of pages.
Dude, I mean, there's so much shit to this.
I'm also not sure where I put the other one.
Don't stress about it too hard, man.
Okay.
Let
me just pull it up in the book and then I can explain it from
there. I'm at Lenz's Law right now. Lagging current. Like, yeah, half the time I don't know if what Roland's talking about is relevant to what we're even doing. Because he talks about, like, you won't understand this right now, but you'll understand this later. And it's like, what?
Okay, here's the section on time constants. I think this is relating to... Oh, no, this was for inductors too. Okay, I thought this was for capacitors. Yeah, so I did actually have this wrong.
I found time constants in chapter 4. It's on page 76.
Yeah, so basically, the time constant is basically the amount of time it takes for the current to reach its maximum point before it starts to drop back down again. And this is specifically for inductors. Which is why the formula includes, henries in the calculation, your inductance.
Right.
So
Okay.
inductance of your inductor divided by the resistance on it is going to be your time constant in seconds.
Cool. Okay. I'm gonna just.
Yeah, there was one previous chapter, I forgot which one, but it uses a really similar formula for the time constant for I believe the voltage, if I'm remembering right. But we don't need to worry about that right now. Okay, what was another one?
Let's see. Well, just clicking through the next question 23 is, but this is just plugging in numbers into
Yeah,
the
that's literally
formula.
just plug and play for your time constant formula.
Yeah. Okay, now like 24, the circuit shown is a total current of 3 amps. What is the approximate current at 2 time constants?
Right, so I should probably explain a little bit more of the time constants. So for the current to reach its maximum, it takes 5 time constants. Within the first time constant, I believe it's 63.
Wait,
Let me just double check.
what?
Okay, so between time constant 0, where no time has passed, and that first time constant, the current will reach 63.2% of its maximum current. Within
Okay.
the second time constant, it'll increase by 63.2% of whatever left is needed for it to reach its maximum.
All right, say that again.
This
But
is a hard one. Let me draw this down.
Did you find? Okay, so you found that in the book.
Let me draw this out here. Okay, so I'm just going to make a crude graph here. Same principle as the time constant for voltages from that previous chapter. Okay, so let's just suppose, all right, so we've got our time constant t. There's 0, 2, 3, 4, not exactly at a perfect scale. Okay, so here's your five time constants, and then you've got your current, and I'm just going to show it by percentages. Here's 20%, 40%, 60%, 80%, 100%. So within the first time constant, by the time it hits there, it reaches 63.2% of its maximum current flow. So it's going to be something like, if I were to draw it out in a line, it'd be kind of like that. So there's still, within that first time constant, there's still 36.8% left between here and here, right?
Okay.
So when it hits the second time constant,
Yeah.
it will rise by another 63.2% of the remaining
I see.
amount
Okay.
that's needed to hit 100%. So by the time you get to that second time constant, it's going to reach, let me check the table here so I don't get it wrong. Where's the actual table? I'm trying to find it.
It's on page 77. There's a time constant table.
Oh,
It has 5 time constants.
I need the like actual percentages and averages. Oh, here's one on
Yeah,
this page. I found
it's
one.
using amperes.
Okay, so by the time you hit the second time constant, you're gonna hit 86.4%. So it's gonna be about there. So you can see it kind of slows down over time.
Yeah, so we get this arc.
And then by the time you get to the third time constant, it's going to be 94.99. So effectively, it's going to be like about 95-ish. It's going to look like that. And then fourth time constant, it's going to be 98.15%. So it's going to be even closer. And then by the time you hit the fifth time constant, it's going to be 99.3%, which is, by the book, it says, that's basically effectively your maximum current. So the curve is going to look like that over the duration of whatever one-time constants, or not one-time constant, what 5-time constants is. That's what your current will look like.
Okay. So basically, oh my god, this is so fucking gay.
Now, another thing to note is that when it goes from its maximum back down to 0,
that's the delay, right?
Sorry, what?
I'm sorry, the decay, not delay.
Yeah,
decay.
So the decay is instead of it being the inverse of this, it's actually.
I see that graph on page 76.
So when it's decreasing, it actually decreases like that. So it'll actually drop by 63%, 63.2% when it's going back down. And
so 63.2% is the number.
Yeah, it's the number. And in fact, one of the quiz questions will ask you specifically for that percentage that the current will drop or increase by within each time constant.
Okay, so, and this is the information I need to solve this problem.
Yeah.
So let's see, what is this problem?
In fact, you know what? Let me make up a quick problem for you to do, or at least I'll do it with you.
Well, I'm looking at the quiz right now in question 24, and I don't have an answer for it. So
yeah, okay. I'm going to do an example of that exact problem so you can understand how to solve it.
Okay, yeah.
Okay, so current. Okay, so let's say we've got a circuit that's got 5 amps, and we want to know what that amperage is at about, I don't know, 3 time constants.
At the third time constant.
Yeah, the third time constant.
Okay.
So let me grab my calculator real quick. We'll basically just draw a little table here. So we'll do T1, T2, T3. Okay, so at T1, we're going to have 63.2% of the maximum, which is, in this case, it's going to be 5 amps.
Okay.
So 63.2 times 5 divided by 100. So 3.16 amps. And our remainder to our max is going to be obviously 5 minus 3.16. So we've got a remaining 1.84 amps before we hit our maximum. Time constant 2, it's going to increase by another 63.2% of our remainder here.
Okay.
So we take 63.2% of our remainder, which is 1.84. And that is
1.16.
Yeah, 1.16288 amps. So it's going to increase by that much at time constant 2. So we take this increase and we add it to time constant 1. That gives us about 4.32. Do you see how this works?
Hang on, I think so. I was trying to do the math while you did it.
Oh, okay.
Yeah, sorry. So I missed how you did it. Give me a second, because this table in the book is different than how you're doing it. It's weird.
Yeah, it's yeah, that
they
table doesn't do the best job of explaining.
Well, they multiply 63.2 times the amperage, and then they get time constant 1, and then they do the same thing, and then they subtract that amperage at time constant 2 from our total amperage, and then they add it together.
Oh wait, are you looking at table 4-2?
Yeah, on page 77.
Yeah, so that first column is just showing you how much it's increasing by, and then how much it's ending at.
Yeah.
Within that time constant.
Okay, then, yeah, I'm going to disregard this page, and I'm going to start over. So the first thing we do, we're at time constant 1, we have 5 amps, so 63.2 times 5, right? Or did you divide it?
So I took 63.2, I multiplied it by 5, and then divided by 100.
Yeah, divide by 100. Here we go. Yeah. So 3.16. Okay.
3.16. So that's your amperage.
And so 5 minus 3.16 equals 1.84.
Yeah. So that's the remainder, the leftover amount that you still need to reach your maximum current.
Right. Okay. Okay. So then we take 63.2 times 1.84, right?
Mm-hmm.
Okay, and we get 116.228, and then we divide that by 100.
Mm-hmm.
Okay, and we get 1.16288. So, 1.16288. And then we subtract that from 1.84 or from 5?
Neither.
Either?
Neither.
Neither? Okay, so yeah, this is where I'm lost.
So remember, every time the time constant goes up by 1, it's increasing. The current is increasing by 63.2% of the remaining amount of your amperage.
So I'm adding this. Yeah, I'm not subtracting.
You're not subtracting. You're going to add that increase to whatever the amperage was previously at from the last time constant.
Okay, so 1.16288 plus 3.16 is 4.32288.
Yep.
Okay.
So from there, you want to figure out how much more amperage do we need to go up by to hit our max from there.
Okay. Okay, so and I'm not looking at my total amperage when I'm trying to find my remainder, correct?
Yeah,
no, I am.
This 5 amps here is basically this is your maximum point. So you want to take 5 and subtract
minus our answer.
Yeah, minus your amperage here.
So we get 0.67712, right?
Yeah, I just put down 0.68, but yeah, that works too.
Sorry, man.
That's
I
okay.
know it's tedious. Um, okay, so then we go to the next one.
Mhm.
For time constant 3, so 63.2 times point. You're just gonna do 0.68.
Yeah, for my calculation anyway.
Right. Yeah, I'm gonna stick with you. So and then I got 42.976, and then divide that by 100 to get 0.42976.
Yep. So that's how much it just increased by for this next time constant.
All right, so 0.42976. All right, and then I add this to my previous remainder, correct?
Yes. Or
All
not your
right,
previous remainder,
plus.
but your previous amperage.
Okay, yeah, my previous amperage. Okay, so plus 4.322 88, and I got 4.75.
Yep. Here, tell you
All
what.
right,
Go ahead and see if you can get tier time constant 4 too.
all right. So 5 minus 4.75 is 0.25.
Mhm.
25. Okay. So then 63.2 times 0.25 divided by 100, 158.
Yep.
Okay. Plus 0.25, right?
You want to add it to your previous amperage from the previous time.
Fuck, god damn it. I keep wanting to add it to my remainder. So plus 4.75.
Yep.
And that's going to give us 4.908.
Yeah.
908. So 5 minus our answer is 0.092.
Tell you what, go ahead and go for time constant 5 while you're at it.
Yeah, I'll fuck this one up too. It'll be sweet. 0.2 times 0.092. And then divide this by 100. 0.05. I'm just gonna say 0.058.
Yeah, that's what I got.
Yeah, plus 4.908, and we get 4.97 rounded up,
Yeah.
which is fine.
And there you go. That's how you do it.
Oh my god, Nate. I love you. Yeah, you don't even understand, dude. I have been fucking with this graph. I have like just this alone. You have made this make sense to me.
Cool.
Yeah, like your sweet table is like the best. So I'm gonna do this a lot. I'm gonna hardcore practice time constants and work on the concepts of this lesson. And I guess I'll holler at you, and maybe we try to do lessons 2 and 3 next.
Sure.
So we can just
actually, there's one other thing I should go over here because I know a couple of questions are going to cover it. In fact, it's specifically question 25. It's the CEMF, which I think it was short for counter electromotive force. I think. Let me just double check here.
I think you're right. I'm looking in the index. I don't know why Jerome told us to not use the index.
I don't know.
Yeah, counter electromotive force. What page is it? Capacitors. Okay, so page
Oh, wait, I might have it
88.
written down here, actually. Let me just double check.
Okay, so no, this is for inductors. This specific section anyway.
Okay.
So it might be page 46.
Oh wait, no, this is okay. Never mind. This is just asking to drag and drop and identify the letters in the formula.
Yeah.
Okay, that shouldn't be. I mean, you can look that up right in the book and already.
I don't know. Nate, reading's pretty hard for me. I don't.
So, have you gone into lesson 2 at all in terms of the homework?
Yeah, actually, uh, sorry, my parents just got home. Let me grab my paper real quick. Yeah, starting at question 5. You know, just like I'm having a lot of trouble with the math. You know,
5. Okay, so for this
that's
whole
where I've been struggling with.
So for this whole section, all the formulas that you use are all identical to the formulas that you would use with getting things like. Remember how with getting the total resistance in a circuit for series and parallel, you had one formula where you just add up the individual resistances, and then there was that other special formula you would use for all the resistors in parallel.
Yeah, the reciprocate bullshit.
Yeah, it's the same thing. You just need to know which one to apply where. Which I'm pretty sure I
Okay.
actually noted that down in my notes here for quiz number 2.
See, I'm just making sure. So yeah, I'm seeing a bunch of series circuits.
Yeah, so that's 3 inductors in series. So yeah, so the rule for series, for inductors specifically, when you're getting the total inductance.
Hang on, real quick, man.
Okay, yeah, that's for inductance.
Sorry about that. My family's trying to get in here.
No, it's all good. I'm just looking at my notes here to making sure I have this all down right.
No, you're fine, dude. Yeah. You have a good day at work?
Oh yeah. Yeah, we got to bend some steel pipe.
Ooh. Sore arms.
I wasn't fat enough to pull the. I tried using all my body weight. It wasn't enough. Me and my journeyman had to call in 2 other dudes.
Oh man, just not enough ass.
Not enough. I gotta eat more.
Yeah, that like sometimes it's good to be kind of a chunky dude in this field.
Yeah, I've noticed. Right. So when you're looking for total inductance, which is the letter L for measured in henries, whether it's series or parallel, you would use the same formula when you're finding the resistances in a circuit.
So regardless, so the same rules that we would use in series and parallel for resistance is what we use for inductance.
Yeah. So if you want to find LT, your total inductance, it's going to be equal to L1 plus L2 plus L3. That's your series formula. It's literally the same thing if you had resistors in series.
Okay, so just replace resistor with inductance.
Yes.
Okay.
And then parallel, it's the same thing for parallel. It's
The reciprocating method.
LT to the power of -1 is equal to power of L1 to the power of -1 plus L2 to the power of -1 plus L3 to the power of -1. It's the same thing. And then same thing goes also for inductive reactance, which is XL. So for a series circuit, your inductive reactance XL is going to be equal to XL1 plus XL2 plus XL3, and then for this one, it's going to be XL to the power of -1 is equal to XL1 to the power of -1 plus XL2 to the power of -1 plus XL3 to the power of -1. So as long as you've got these formulas, any kind of math problems for homework 2 shouldn't be too difficult. Let me look
Okay,
ahead
I'm
here.
clicking through right now to see if there's anything. What's the total? What's the inductive reactance of L3? Yeah, you can find that using the same method.
Oh yeah, and then another important formula, which is finding inductive reactance specifically. There's a formula for that. So
Okay.
if you want to find your inductive reactance on an inductor, it's going to be equal to times pi times F times L. I believe F was your, yeah, so F being your frequency and L being your inductance.
So you need to find your inductance to find your inductive reactance.
Yes.
Okay. Just writing all this down. Dude, how are you so good at like picking this up?
I've so back in high school, some of this the way I've been learning this is pretty similar to the way I've been learning stuff back in my high school physics class, which is just finding formulas and figuring out which letters represent what and what they're measured in, and
So you're literally just picking and choosing is
sort of.
the when and where is what I'm gathering.
Yeah.
God damn it! Why didn't I fucking think of that? Oh my
Just
god.
learning formulas and knowing when and where to use them.
That's the whole thing.
And
I
then
was
just, understanding like what like the key terms are as well.
yeah, like what is inductive reactance?
So inductive reactance, let me just look it up really quick to be sure. But from what I understand, it's inductive reactance, I believe, was like a natural resistance to inductance. I'm just going to Google it really quick rather than look it up in the book. Changing current flow. Yeah, so the literal Google result says that it's the name given to the opposition to a changing current flow, which is what happens inside of an inductor. So yeah, inductance is it's basically just the natural resistance that occurs inside of an inductor.
Okay. Let's see. I'm flicking through the rest of lesson 2 to see if there was anything. A lot of this is just like terms shit.
Yeah, terms and a little bit of plug and play here.
Yeah, let's see. Okay, so starting at Starting at question 10, we've got some math and shit. So let's see. So these inductors are just in parallel. So you just use the rule for parallel. You got to find your total inductance, and then inductive reactance, and then inductive reactance of L2, and then total inductive reactance. Okay, same deal. That's not that big of a deal. Okay, and then that just wants you to do like the Hertz, blah blah blah. Okay, so pretty much just as long as I use the correct formula, I can figure this out.
Yeah.
Yep. Okay. Chalk one up to Tyler is retarded. Dude, like you have no idea. Like I'm so much better in the field than I am in a classroom. It is fucking sad. Yeah, okay, so that's everything for lesson 2. I'm clicking through lesson 3 right now to see. Let's see. Okay, all this is vocab. Okay, a current has a voltage of 240 volts and an inductive reactance of 30 ohms. What is the current flow?
Which question is that?
That's question 10 on lesson 3.
Okay, so that one's really straightforward. In fact, if you go back to the overview page for lesson 3, your formula is actually right there. So it states that for a resistive circuit that your current is equal to your voltage divided by your resistance for a resistive circuit where you've just got resistors and loads that have resistance in them.
Just like on our circle.
Yeah. So for an inductive circuit, your current I is equal to your voltage divided by your inductive reactance, which is also measured in ohms. So yeah, for question 10, it's just a simple matter of
plug and play.
Yeah, plug and play, knowing this specific little formula right here.
240 over 30. Okay. Let's see. Easy enough. Maybe I should make flashcards so I can.
Yeah, you could
try to bust out these terms. I don't know. Like, Nate, I'm not even gonna bullshit with you. This is the 4th time that I've tried some form of higher education. I'm really like shitty at this.
Huh.
Sorry, I know that you don't care.
Sorry.
You don't give a shit. I mean nothing to you. It's fine. I know that.
Were there any others on lesson 3 stand out to you in particular?
Let's see. A purely inductive 120 volt circuit, 60 hertz draws was the circuit. So I mean, I just use my R formula there, and I have right at number 13.
Number 13. Oh, that was actually one of the questions I got wrong on my first run through.
Okay.
I did screw up on something. Okay, purely inductive 120 volt 60 hertz circuit draws 2.7 amperes. What is the reactance of the circuit? Yeah, so I'm pretty sure what I did. Well, let me just run the calculation for this again really quick, because I'm pretty sure I know what I did where I screwed up and got the completely wrong answer.
Sure. Like, it's the 60 hertz that throws me off. And it just says, what's the reactance, not the inductive reaction. reactants, and I'm not looking for the inductance.
Okay. I'm actually not sure what I did to get this horribly wrong answer when I previously went through here. But your answer actually lies right within this
Same
formula
formula?
here. Same formula, but instead of having your voltage and inductive reactance, you've got your voltage and your current. So in this case, I'll just write it out here real quick. So you can just plug and play literally. 2.7, your amperage,
Okay.
is equal to your voltage, 120 volts, divided by your inductive reactance. And it's literally just simplified to figure out XL right there, and that's it.
Okay. Okay, so the 60 hertz is a red herring
Yes.
in this problem.
That is just to screw with you.
Fuck these people, dude. Jesus Christ.
That's totally something I would do if I had the chance.
You're evil, Nate.
Yeah, I don't know why. This is the only question on the quiz that I actually got wrong when I went through it, and I don't know how I came up with that horribly wrong answer. I somehow came out with 45,000 ohms.
Woo.
Yeah. I don't know what I did. I did not use this formula though. I know that much.
So pretty much everything in this lesson revolves around that formula.
Pretty much. Let me just
Um,
check. You will need to use this formula for at least one problem.
which problem is that? So I can get an
Actually,
number 18, maybe?
2? I see at least 2.
Okay.
It's just a matter of looking at what values they give you and what they want, and then just looking at your formulas and seeing how many of these values you can fill in given your given information, and seeing if the value you need is also included in that formula.
It goes back to plug and play and learning the terms.
Mm-hmm.